Bismillahirrahmanirrahim. In this video we will discuss about the arithmetic and logical operator Verilog HDL code. In the previous video we will just discuss the basic concept of arithmetic and the logical operators. Now we perform some exercise problems. We have to evaluate the logical NOT of the 67. 67 is a 8-bit binary number. Now in the we run this and type this again. Every module we write the file name here and declare the variables A and B. A and B are the variables. Now we declare the input. Input is equal to 8-bit input, and so we write it 0 to 7 and here. Similarly, the output is also the 8-bit. We write it 0 to 7. Now we declare A is equal to 67. We assign B is equal to A not, and we end the module here, and here we write value 8 0. We understand this by the RTL view, and we run this study. We show some error. Here we did the mistake here. We have to look at this with semicolon. Now we run the study again. Here the message it will take some time to compile. Here we can see that the full compilation was successful. Now we go to the RTL view. Here is the RTL view. The input is 8-bit, which is equal to 00. 67 into binary is 0100 0011. 0100 0011. When it goes here, it shows the 1, and when it passes through the NOT gate, the value is shown 0. So from here we evaluate 0. We can see this also in the universal program BWF. Simply we insert the node here, list it here and copy it. Click on OK. Here A is the input. We write it into binary form 0100 0011. Now we convert it into unsigned decimal, which is equal to 67. Now we run the study. Now we can see this here. In the A is the input, which is equal to 67, and output is equal to 8-bit output, and it will show the 00000 according to our requirement. That's all for this problem. Now in second problem, 0, logical, and 1. We declare the 0, A is equal to 0 and B is equal to 1 in the logical code, Verilog code. Now we go to the software, and here we write the module, file name, and declare the variables. Let A, B, and C are the variables. We declare the input. Input is 3. We have 4-bit inputs, so we write it 3 to 0. 3 to 0. Let A and B are the inputs. Now we go to the output. Output is also 4-bit, 0 to 3. Let's see the output. A is equal to 0 and B is equal to 1. Now we assign. Here we can see it is A is equal to 0 and B is equal to 1. A logical and B. We similarly write here C is equal to A logically and B, and we run the module here, end the module here, end module, and here we assign, here we write it a value 8, 0, because 0 when 0 multiplied by every number, it become also 0. A is equal to 0 and B is equal to 1. 1 multiplied by 0 is equal to 0. So now we run this. We write it x1 b. It takes some time to compile. You can see here. Now we can see that full compilation was successful. Now for the RTL view, we go to the RTL view. Here is the RTL view of this circuit. A and B are the 4-bit inputs, pass through the OR gates, and then both the output of the OR gates are multiplied by the AND gates, and here is the output will also be the 4-bit output. Now we go to the waveform, universal program VWF. Here we insert the node finder and list it here and copy, and okay. Here we can see that A and B are the A will be 0 and B is equal to 1. And now we convert. Now we run the study. it will take some time to compile. The message is shown here. We can see this, it shows the compilation. When 0 multiplied by 1, it shows the 0 0. We can also convert this into the unsigned decimal 0 1 0. Now we go to the next task, which is 1 logical or 2. We declare a is equal to 1 and b is equal to 2. We go to the software. Here we create the Verilog HDL file and we write the program. Here we simply module, file name, and declare the variables. Let a, b and c are the variables. Here we declare the input. We have the 4-bit inputs, so we write it 0 to 3. A and B are the inputs. Now we declare the output. Output is also 4-bit and C is the output. Here we assign A is equal to, we can see it here, A is equal to 1 and B is equal to 2. A is equal to 1 and B is equal to 2. Now we assign C is equal to A logical or B. Now here we end the module here. It evaluates 1 or 2 evaluates 1. We can prove this from the waveform. For the RTL view, first we run the study here. We can see that the full compilation was successful. Now we go to the RTL view. Here is the RTL view. We can see that here is the 4-bit input and output passed through the OR gate and create the output also of 4-bit. Now we go to the University program VWF and we insert the nodes here. We insert the node here, listed it here, and click on OK. We can see there A and B are the inputs and C output. We assign the value. A is equal to 1 and B is equal to 2. We write it in the binary form. We can also convert this into unsigned decimal. Now we run the study. Here we can see that the output, when it shows the 1, we also convert into unsigned decimal and we convert it into we can also convert it into binary. That's all for this, and we'll now in the next task D, we have the two inputs A and B. We suppose A is equal to 0 and B is equal to 1. When 1 and logical and 1 multiply is become 1, and then 1 and 0 operates, it becomes 1 or 0 1, and when 1 is or logically or with the not 1, it also becomes 1. So its evaluate finally the 1. We can see this in the software. Go to the Verilog HDL file. Here we write the module name ex1d and declare the variables. A, B and C are the variables. Now we declare the input. Four-bit inputs. A and B are the inputs. Similarly, we declare the output. Output is also 4-bit 0 to 3. Here we write A is equal to 0 and B is equal to 1, and assign here C output is equal to, here we can see that 0 is equal to A and 1 is equal to B. A or B logical and B. We can write here B and B, and here or A or logically B and or logically not 1. Go to the here or and logically not A. That's the main body of the program. Here we end the module. End module. Here. Now we run the study. It takes some time to compile. It shows some error. We can see here. Here we write the B capital. We write in the short form. Now we run this again. Analysis, elaboration and analysis synthesis done successfully. Now it compiling the program. It will take some time to compile. Here we can see that the full compilation was successful. Now we go to the RTL view. Here is the RTL view of this. Here A and B are the inputs. Here A is also a 4-bit input and B is also a 4-bit input, and output will also be a 4-bit. Here is the RTL view. Now we go to the universal waveform, University Program VW. Here we insert the node finder and go to the list, copy it here and click on OK. Here we A is equal to 0, we can leave this as, and B is equal to 1, as this one, and we convert both of them into unsigned decimal. 0 and 1. Now we compile, simulate this. Here we can see the simulation flowing. Here is the output of this. We can see that the output is, it evaluates 1. We write it here also, evaluates 1. Now we go to the next problem. Here next problem is what value of the gamma is displayed if following module is running. This is the module. We simply copy it here. And go to the software. Here we create the Verilog HDL file, and okay, here we copy it, paste it, and run the study. Save it on desktop. During compilation, we study their behavior. Here is some problem. We change the name of the file ex1e, and here it declare the variables alpha 2, beta, and gamma. Input is beta, output is alpha 2, and it has two output, alpha 2 and gamma. It declares beta is equal to 1, binary 0, so and assign the alpha is equal to logically not beta, and secondly assign the gamma is equal to alpha 2 logically or beta. So now we study their behavior, run the study. Take some time to compile as shown. Now we can see it here, the full compilation was successful. We go to the RTL view. Here is the RTL view. It's not so much clear. In assign alpha 2 output, it simply converts the beta, and in gamma it takes the output alpha 2 and convert it into binary 2. In this in alpha 2 converts the input by NOT gate. Here circle show the NOT gate. And in gamma it takes the output from alpha 2 and by the sum it shows the output. Now we go to the university program VWF. Here we insert the node finder, list it here and paste OK and OK. Here is the waveform. We first increase the time period 10 to 50. To 100 to the 200. That's the waveform of the gamma. Here beta is the input and alpha 2 act as both input and output. Basically it's our output, and gamma is the main output. We have to study the behavior of this. That's all. The exercise 1. In the next video we will study the relational behavior of relational operators in the Verilog code. That's all for now. Here we can see that the question is what value of gamma display if the value of model is 1. The values given in this is equal to beta is equal to 1, binary is 0. Now we go to the waveform. Beta is equal to binary 0. Now we run the study. What will be the output when the beta is equal to 0? It takes some time to simulate, and here it shows the output gamma B1. And that's our question is to find the value of the gamma, and the value of gamma is equal to 1. Now we write it here. It's evaluate 1. That's all for this video.